Stars, those brilliant points of light that have fascinated humanity for millennia, are often seen as eternal, unchanging fixtures in the night sky. But what if I told you that stars are far from immortal? They live, they evolve, and yes, they even die, leaving behind a legacy that shapes the very fabric of the universe. This is the story of stellar metamorphosis, a process as dramatic and transformative as life itself. From the fiery birth of a star in the heart of a collapsing cloud of gas and dust, to its eventual death as a fading ember or a spectacular supernova, the life cycle of a star is a cosmic dance of creation and destruction. But what happens when a star dies? How does its death give rise to new worlds, new possibilities, and even the building blocks of life itself? In this video, we'll explore the incredible journey of stars, how they're born, how they evolve, and how their deaths leave an indelible mark on the cosmos. Together, we'll uncover the forces that drive their evolution and the mysteries they leave behind, painting a picture of a universe that is as dynamic as it is beautiful. So, are you ready to dive into one of the universe's most profound secrets? Let's begin. Deep within the vast, swirling clouds of gas and dust known as nebulae, the story of a star begins. These cosmic nurseries, often illuminated by the faint glow of other stars, are the birthplaces of stellar life. Imagine a place where the universe itself seems to gather its breath, preparing to create something extraordinary. It all starts with gravity, the silent, relentless force that pulls together particles of gas and dust, compressing them into dense, hot cores. Over thousands, even millions of years, these cores grow denser and hotter until the moment arrives when nuclear fusion ignites. This is the spark of a star's life, the moment when hydrogen atoms collide at unimaginable pressures, fusing into helium and releasing a burst of energy that lights up the cosmos. The birth of a star is nothing short of a cosmic miracle. Picture it, a glowing ember emerging from the darkness, its light piercing through the surrounding gas and dust like a beacon in the void. This is the moment a star is born, not just as a ball of gas, but as a source of light and energy that will shape its corner of the universe. These newborn stars are the universe's way of seeding itself with the building blocks of planets, moons, and even life. They are the engines that power galaxies, the creators of elements, and the architects of cosmic evolution. But this is only the beginning. Once a star ignites, it embarks on a journey that will span billions of years, a journey filled with transformation, struggle, and ultimately, renewal. From the fiery cradle of its birth, a star will grow, burn, and eventually face its end, a process as inevitable as it is awe-inspiring. And just as its birth shapes the universe, so too will its death leave a lasting legacy. But before we explore the life and death of stars, let's take a closer look at how these celestial giants are born and the incredible forces that bring them into existence. After all, every story has a beginning, and for stars, it all starts in the heart of a nebula. Once a star ignites and begins its life, it enters a phase of stability and balance known as the main sequence. This is where stars, including our own sun, spend the majority of their existence burning brightly and steadily, like cosmic lighthouses in the vast ocean of space. During this phase, the star's core becomes a powerhouse of nuclear fusion, where hydrogen atoms collide under immense pressure and heat, fusing into helium and releasing an extraordinary amount of energy. This energy radiates outward, countering the relentless pull of gravity that seeks to collapse the star inward. It's a delicate dance, a cosmic tug of war that keeps the star in equilibrium, neither collapsing nor exploding, but shining with a steady brilliance. Take our Sun, for example. It's a main sequence star and has been for about 4.5 billion years. Every second, it converts millions of tons of hydrogen into helium, releasing enough energy to sustain life on Earth and illuminate our solar system. Without this stable phase, life as we know it wouldn't exist. The Sun's consistent output of light and heat creates the conditions necessary for planets like ours to thrive, making the main sequence phase not just a scientific curiosity, but a cornerstone of our very existence. But this stability isn't infinite. Even stars, with all their power and longevity, can't remain in this phase forever. Over time, the hydrogen fuel in their cores begins to deplete, and the balance between gravity and radiation starts to shift. This marks the beginning of the end for a star's time on the main sequence, setting the stage for the next chapter in its life. What happens next depends on the star's size and mass factors that determine whether it will fade quietly into the cosmos or go out in a blaze of glory. For now, though, let's appreciate the main sequence for what it is: a period of cosmic harmony where stars shine steadily, giving light, warmth, and the promise of possibility to the universe around them. As we move forward, we'll explore what happens when this balance is disrupted and how stars evolve beyond their prime. But for now, let's linger a little longer in this phase of stability, where stars like our Sun remind us of the delicate and beautiful forces that shape the universe. As the life of a star unfolds, one factor plays a decisive role in shaping its destiny: its mass. The amount of matter a star contains isn't just a number, it's a cosmic blueprint that dictates how the star will live, evolve, and ultimately meet its end. From the smallest red dwarfs to the most massive blue giants, a star's mass determines everything from its brightness and temperature to its lifespan and the manner of its death. Let's start with the smaller stars, the red dwarfs. These stellar underdogs, often no larger than a fraction of our Sun's mass, are the marathon runners of the cosmos. They burn their fuel slowly and steadily, conserving their energy over trillions of years. Imagine a candle flickering in the dark, glowing faintly but persistently. That's a red dwarf, unyielding, enduring, and remarkably efficient. Because their cores are less massive, the pressure and heat needed for nuclear fusion are lower, allowing them to stretch their hydrogen fuel far longer than their larger counterparts. For these stars, life is a long, quiet journey, one that outlasts even the oldest galaxies. On the other end of the spectrum are the high-mass stars, the blue giants. These cosmic titans are the sprinters of the universe, burning through their fuel at a breakneck pace. With masses many times that of our Sun, their cores are under immense pressure, driving nuclear fusion at an extraordinary rate. Think of a firework exploding in the night sky: spectacular, intense, but fleeting. Blue giants shine with a brilliance that outshines entire galaxies, but their lives are measured in mere millions of years, not billions. The sheer force of their fusion reactions creates heavier elements like carbon, oxygen, and even iron, which are later scattered into space when these stars meet their dramatic ends. The difference in mass doesn't just affect how long a star lives, it also determines how it dies. Low-mass stars, like red dwarfs, fade slowly and quietly, cooling into dim embers known as white dwarfs. High-mass stars, however, go out in a blaze of glory. When their fuel runs out, their cores collapse under their own gravity, triggering a cataclysmic explosion known as a supernova. These explosions are so powerful they can outshine entire galaxies, leaving behind remnants like neutron stars or black holes. Mass, then, is the great divider in the stellar world. It shapes not only the life of a star, but also the legacy it leaves behind. Whether a star fades gently or explodes spectacularly, its mass is the key to understanding its journey. And as we look deeper into the lives of stars, we'll see how these transformations, quiet or explosive, shape the universe itself. But what happens when a star's fuel begins to run low? How does it adapt to the changes within its core? And what dramatic transformations await as it ages? The answers lie in the next chapter of a star's life, where even the most stable stars face the inevitable shifts that come with time. Let's explore what happens when the balance of fusion and gravity begins to falter, and the star's story takes a turn toward its final act. As a star ages, the balance that once defined its existence begins to shift. For billions of years, stars like our Sun burn steadily, fusing hydrogen into helium in their cores. But eventually, the hydrogen fuel runs low, and the star must adapt to survive. This is the moment when a star enters one of the most dramatic and visually stunning phases of its life, the red giant or supergiant stage. When a star exhausts the hydrogen in its core, the delicate equilibrium between gravity and radiation starts to falter. Gravity, always pulling inward, causes the core to contract, increasing its temperature and pressure. But while the core grows hotter, the outer layers of the star react in the opposite way. They expand, swelling to enormous sizes as the star begins to burn hydrogen in a shell around the core. The result is a star that grows hundreds, even thousands of times larger than its original size. This transformation is nothing short of breathtaking. Picture a star that once shone with a steady, white light now glowing with a deep red hue, its surface cooling as it expands. These red giants and supergiants are among the largest and most luminous objects in the universe. Take Betelgeuse, for example, a red supergiant in the constellation Orion. If placed at the center of our solar system, its outer layers would stretch beyond the orbit of Jupiter, engulfing planets and dwarfing the Sun in both size and brightness. The changes in temperature and color during this phase are striking. As the star expands, its surface cools, shifting from the white or yellow light of its main sequence days to a reddish glow. But don't let the cooler surface fool you. The core is hotter than ever, reaching temperatures that can ignite the fusion of heavier elements like helium. This creates a star that's both massive and luminous, a beacon in the night sky that captures the imagination of astronomers and stargazers alike. Yet, even these giants are not immortal. The red giant or supergiant phase is a star's last hurrah, a final act of cosmic brilliance before the inevitable end. The outer layers, now vast and tenuous, are held loosely by gravity, ready to be shed into space. Meanwhile, the core continues to contract, setting the stage for the star's ultimate fate. What happens next depends on the star's mass. For smaller stars, the outer layers drift away, leaving behind a glowing core that will eventually cool into a white dwarf. For more massive stars, the core's collapse triggers a cataclysmic explosion, a supernova, that will light up the galaxy and scatter its remnants across the cosmos. But before we explore those explosive finales, let's take a moment to appreciate the grandeur of these aging stars, whose immense size and luminosity remind us of the incredible scale and beauty of the universe. The red giant and supergiant phases are a testament to the dynamic nature of stars. They show us that even in the vastness of space, change is constant and transformation is inevitable. As these stars swell and glow, they remind us that the universe is a place of endless wonder, where even the end of one story can lead to the beginning of countless others. As the red giant phase comes to an end for low-mass stars, the universe prepares to reveal one of its most breathtaking spectacles, the formation of planetary nebulae. These glowing clouds of gas and dust are the final breath of stars like our Sun, a last act of cosmic artistry before they fade into the quiet twilight of their existence. But what exactly happens during this stage, and why are planetary nebulae so significant? When a low-mass star exhausts its nuclear fuel, its outer layers, once held in place by the delicate balance of gravity and radiation, begin to drift away. This process isn't sudden or violent. It's more like a slow, gentle exhale as the star releases its outer envelope into space. These layers, rich in elements like carbon, nitrogen, and oxygen, expand outward, forming a glowing shell around the star's exposed core. At the heart of this shell lies the star's core, now a dense, hot remnant known as a white dwarf. Though small, this white dwarf is incredibly hot, radiating ultraviolet light that illuminates the surrounding gas. This light energizes the ejected material, causing it to glow in vibrant colors and intricate patterns. The result is a planetary nebula, a cosmic masterpiece that can take on a variety of shapes: rings, spirals, or even delicate, wispy tendrils. One of the most famous examples is the Ring Nebula, a glowing halo of gas that resembles a celestial smoke ring. Its symmetrical structure and vivid colors make it a favorite among astronomers and stargazers alike. But what makes planetary nebulae so much more than just beautiful objects? They play a crucial role in enriching the universe. The material ejected by these stars contains heavy elements forged in their cores during their lifetimes. These elements, including carbon and oxygen, are the building blocks of planets, moons, and even life itself. Without planetary nebulae, the universe would lack the diversity of elements necessary to form complex structures and sustain life as we know it. As the white dwarf cools over billions of years, the planetary nebula gradually fades, its material dispersing into the interstellar medium. But the legacy of the star lives on, as its enriched gas becomes part of future generations of stars, planets, and possibly even life. Yet, not all stars end their lives so peacefully. For high-mass stars, the journey concludes with a far more dramatic finale, one that reshapes the cosmos in ways even more profound. These stars don't quietly exhale their outer layers. Instead, they go out in a blaze of glory, lighting up the universe with one of the most powerful events imaginable, a supernova. As we turn our attention to these explosive deaths, we'll see how the universe's most massive stars leave behind a legacy that's as violent as it is transformative. But for now, let's take a moment to appreciate the quiet beauty of planetary nebulae, the final breath of stars that have given so much to the cosmos. For high-mass stars, the end is anything but quiet. These colossal giants, born with masses many times greater than our Sun, meet their fate in one of the most violent and spectacular events in the universe, a supernova. This isn't just a star's death, it's a cosmic eruption, a burst of energy so immense it can outshine entire galaxies for weeks. But what exactly triggers this cataclysmic event, and why does it matter so much to the universe? The story of a supernova begins deep within the star's core. For millions of years, these massive stars burn through their fuel at a staggering rate, fusing lighter elements into heavier ones, first hydrogen into helium, then helium into carbon, and so on, all the way up to iron. But iron is different. Unlike the lighter elements, iron doesn't release energy when fused. Instead, it absorbs it. This marks a turning point. When the core fills with iron, fusion stops, and the star's internal support system collapses. Gravity, no longer counteracted by the outward pressure of fusion, takes over. In an instant, the core implodes, collapsing inward at speeds approaching a quarter of the speed of light. The resulting shockwave races outward, blasting the star's outer layers into space with unimaginable force. This is the supernova, a titanic explosion that scatters the star's remains across the cosmos, seeding the universe with the heavy elements forged in its core. The energy released in a supernova is almost beyond comprehension. In a single moment, a star can emit more energy than our sun will produce in its entire lifetime. This energy drives the creation of elements like gold, silver, and uranium, elements that are essential not just for planets and moons, but for life itself. Without supernova, the universe would lack the diversity of materials needed to build complex structures, including the very atoms that make up our bodies. One of the most famous examples of a supernova remnant is the Crab Nebula. In the year 1054, Chinese astronomers recorded a guest star in the sky, a supernova so bright it was visible during the day for weeks. Today, the Crab Nebula is a glowing, expanding cloud of gas and dust, the aftermath of that ancient explosion. At its heart lies a neutron star, a dense remnant spinning rapidly and emitting pulses of radiation. This remnant is a testament to the power of supernova, a reminder of how even in death, stars continue to shape the universe, but the story doesn't end with the explosion. The material ejected by a supernova spreads through space, enriching the interstellar medium with heavy elements. Over time, this material becomes part of new stars, planets, and even living organisms. In a very real sense, we are made of stardust, forged in the hearts of stars and scattered across the cosmos by their explosive deaths. As we move forward, we'll explore what remains after the dust settles: neutron stars and black holes, the ultimate remnants of these cosmic giants. But for now, let's take a moment to marvel at the sheer power of supernova, events that remind us of the universe's capacity for both destruction and creation. These explosions are not just the end of a star's life, they are the beginning of countless new possibilities, a testament to the interconnectedness of all things in the cosmos. When a massive star goes supernova, the explosion doesn't just scatter its outer layers into space, it leaves behind something extraordinary at its heart. This is the birth of a neutron star, one of the most bizarre and fascinating objects in the universe. Imagine taking the mass of the sun and squeezing it into a sphere no wider than a city. The result is a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. Neutron stars are born from the collapsed cores of massive stars that have exhausted their nuclear fuel. When the core can no longer support itself against gravity, it implodes, crushing protons and electrons together to form neutrons. This process creates an object with a density so extreme that it defies comprehension. If you were to stand on the surface of a neutron star, something that's impossible, of course, due to its crushing gravity, you'd experience forces strong enough to flatten atoms into a thin paste. But it's not just their density that makes neutron stars remarkable. Many of them spin at incredible speeds, rotating hundreds of times per second. This rapid rotation, combined with their intense magnetic fields, can produce beams of radiation that sweep across the sky like cosmic lighthouses. When these beams point toward Earth, we detect them as regular pulses of light, earning these neutron stars the name pulsars. One of the most famous pulsars is the Crab pulsar, located at the heart of the Crab Nebula. Spinning 30 times per second, it emits pulses of radiation across the electromagnetic spectrum, from radio waves to gamma rays. This pulsar is a direct remnant of the supernova observed by Chinese astronomers in 1054, a living testament to the explosive power of stellar death. Neutron stars also boast some of the strongest magnetic fields in the universe, trillions of times more powerful than Earth's. These fields can accelerate particles to near light speeds, creating spectacular phenomena like magnetars. Neutron stars with magnetic fields so intense they can distort the very fabric of space-time. Despite their small size, neutron stars play a crucial role in the cosmos. They are laboratories for extreme physics, offering insights into the behavior of matter under conditions that can never be replicated on Earth. Their formation also enriches the universe with heavy elements, as the intense heat and pressure during their birth forge elements like gold and platinum, which are later scattered into space. Yet, as remarkable as neutron stars are, they are not the final chapter in the story of stellar remnants. Beyond them lies an even more mysterious and enigmatic phenomenon, one that defies our understanding of space, time, and gravity itself. These are black holes, the ultimate endpoint for the most massive stars, and perhaps the most intriguing objects in the universe. As we turn our gaze toward these cosmic enigmas, we'll explore how black holes form, what makes them so unique, and why they continue to captivate the imagination of scientists and stargazers alike. But for now, let's take a moment to appreciate neutron stars, the dense, spinning remnants that remind us of the incredible forces at play in the universe. They are a testament to the extremes of nature, a glimpse into a world where the rules of physics are pushed to their limits. Among the many wonders of the universe, few captivate the imagination like black holes. These enigmatic objects are the ultimate cosmic mystery, born from the collapse of the most massive stars. When a star many times heavier than our Sun exhausts its fuel, it doesn't just go supernova, it leaves behind a core so dense that nothing, not even light, can escape its gravitational pull. This is the birth of a black hole, a region of space where the laws of physics as we know them begin to break down. At the heart of a black hole lies the singularity, a point where matter is crushed to infinite density and the fabric of space-time becomes infinitely curved. Surrounding the singularity is the event horizon, the boundary beyond which nothing can escape. Think of it as a cosmic point of no return. Once something crosses this threshold, it's gone forever, swallowed by the black hole's immense gravity. To visualize this, imagine a waterfall. The event horizon is like the edge of the falls. Once you pass it, there's no climbing back up, but black holes aren't just cosmic vacuum cleaners. They play a crucial role in shaping the universe around them. Supermassive black holes, millions or even billions of times more massive than our Sun, are thought to reside at the centers of most galaxies, including our own Milky Way. These colossal objects influence the motion of stars and gas around them, helping to shape the structure and evolution of entire galaxies. Without them, the universe as we know it might look very different. What makes black holes even more fascinating is their potential to challenge our understanding of reality. Some theories suggest they could act as gateways to other dimensions or universes, offering a shortcut through the fabric of space-time. While this idea remains speculative, it sparks the imagination and reminds us of how much we still have to learn about the cosmos. The formation of a black hole marks the end of a star's life, but it also represents a new beginning. As these objects interact with their surroundings, they can trigger the birth of new stars and influence the evolution of galaxies. In a way, black holes are both destroyers and creators, embodying the dual nature of the universe itself. Reflecting on the broader implications of stellar death, we see a universe that is constantly transforming, from the birth of stars in nebulae to their dramatic deaths as supernova or black holes. Each stage of a star's life contributes to the intricate dance of creation and destruction that shapes the cosmos. As we continue to explore these mysteries, we gain not only a deeper understanding of the universe, but also a greater appreciation for our place within it. But the story doesn't end here. Beyond black holes lies another realm of cosmic wonder, where the remnants of stars continue to shape the universe in ways we are only beginning to understand. Let's turn our attention to what happens after the dust settles and how the legacy of stars endures long after their light has faded. The universe operates like a vast, interconnected ecosystem where nothing is truly lost, only transformed. When stars die, they don't simply vanish into the void. Instead, they leave behind a legacy, scattering the elements they've forged throughout their lives into the cosmos. This process, known as cosmic recycling, is the engine that drives the evolution of the universe, creating the building blocks for new stars, planets, and even life itself. Think of it this way: every star is like a cosmic factory, fusing lighter elements into heavier ones in its core. From hydrogen to helium, helium to carbon, and so on, each stage of a star's life contributes to the creation of elements essential for the universe's complexity. But it's in their deaths, whether through the gentle shedding of planetary nebulae or the explosive fury of supernova, that stars truly give back to the cosmos. These events release a rich mix of elements into space, from the oxygen we breathe to the iron in our blood, seeding the interstellar medium with the raw materials for future generations of stars and planets. This cosmic recycling process is beautifully illustrated by the life cycle of our own solar system. The Sun, along with its planets, formed from a cloud of gas and dust enriched by the remnants of ancient stars. Every element on Earth, from the calcium in our bones to the gold in our jewelry, was forged in the heart of a star or scattered by a supernova explosion. Even the carbon that forms the backbone of life itself owes its existence to the death of stars. In this way, the universe resembles a vast, self-sustaining ecosystem. Stars are born, live, die, and give rise to new stars, creating a cycle of creation and renewal that spans billions of years. Each generation of stars builds upon the work of the last, enriching the cosmos with heavier elements and paving the way for greater complexity and diversity. This interconnectedness isn't just a scientific concept, it's a reminder of our own place in the universe. The atoms that make up our bodies were once part of stars that lived and died long before our solar system existed. In a very real sense, we are stardust, the product of a cosmic process that has been unfolding since the dawn of time. Understanding stellar metamorphosis, the life, death, and rebirth of stars, gives us a key to unlocking the mysteries of the universe's evolution. It shows us how the cosmos transforms itself, creating the conditions for galaxies, planets, and life to emerge. And as we continue to explore the universe, we're not just learning about distant stars and galaxies, we're uncovering the story of our own origins, written in the light of countless suns. As we look ahead, let's consider how this knowledge shapes our understanding of the universe's past, present, and future. What does the cycle of cosmic recycling tell us about the fate of galaxies, the potential for life elsewhere, and the ultimate destiny of the cosmos itself? These are the questions that drive us forward, inspiring us to explore the universe with curiosity, wonder, and a deep appreciation for the interconnectedness of all things. Galaxies, Those vast, swirling collections of stars, gas, and dust are more than just static snapshots of the universe. They are dynamic, ever-changing systems shaped by the lives and deaths of the stars within them. The process of stellar metamorphosis, from the birth of stars in nebulae to their explosive deaths as supernova, plays a crucial role in shaping the structure and evolution of galaxies. It's a story of creation and destruction, where the end of one star's life becomes the beginning of countless others. Take the Milky Way, our own galactic home, as an example. This sprawling spiral galaxy, with its billions of stars, didn't form all at once. Instead, it grew over billions of years, shaped by the cycles of stellar birth and death. When massive stars explode as supernova, they send shockwaves through the surrounding gas and dust, compressing it and triggering the formation of new stars. These stellar winds and explosions act like cosmic sculptors, carving out regions of star formation and enriching the interstellar medium with heavy elements. But the influence of stellar metamorphosis doesn't stop there. Black holes, the remnants of the most massive stars, also play a pivotal role in galaxy evolution. At the heart of the Milky Way lies Sagittarius A, a supermassive black hole with a mass millions of times that of our Sun. This colossal object doesn't just sit idly, it actively shapes its surroundings. As it pulls in gas and dust, it releases vast amounts of energy, heating the surrounding material and regulating the growth of the galaxy. In this way, black holes act as cosmic regulators, balancing the forces of creation and destruction. The interplay between stars and galaxies is a delicate dance. Supernova seed the galaxy with the elements needed for new stars and planets, while stellar winds and radiation clear out regions of space, allowing fresh cycles of star formation to begin. Over time, these processes create the intricate structures we see in galaxies today: spiral arms, dense star clusters, and vast clouds of gas and dust. This ongoing cycle of stellar life and death doesn't just shape galaxies, it also influences the formation of planetary systems. When a star dies, it scatters its enriched material into space, providing the raw ingredients for new planets. The planets in our solar system, including Earth, owe their existence to the remnants of ancient stars. Every rock, every drop of water, and every breath of air contains atoms forged in the hearts of stars that lived and died long before the sun was born. As we reflect on the role of stellar metamorphosis in galaxy formation, we see a universe that is deeply interconnected. The life and death of stars are not isolated events, they are part of a grand, cosmic cycle that shapes the very fabric of the cosmos. From the birth of new stars in the wake of supernova to the influence of black holes on galaxy growth, every stage of stellar evolution leaves its mark on the universe. But the story doesn't end here. As we look deeper into the cosmos, we'll explore how these processes extend beyond galaxies, influencing the large-scale structure of the universe itself. The legacy of stars is not confined to their immediate surroundings. It ripples across the cosmos, shaping the destiny of everything within it. And as we continue to unravel these mysteries, we gain a deeper understanding of the forces that have shaped our universe, from its earliest moments to the present day. The story of stellar metamorphosis doesn't end with the death of a star, it's just the beginning of something new. When stars die, they don't simply disappear, they leave behind a cosmic legacy, scattering the elements they've forged into the universe. These remnants become the building blocks for planets, moons, and even the potential for life. But how exactly do the ashes of dying stars transform into worlds like Earth? Let's take a closer look at the incredible process that connects the death of stars to the birth of planets. When a star exhausts its fuel and reaches the end of its life, it releases a wealth of heavy elements into space. These elements, carbon, oxygen, silicon, iron, and more, are the raw materials for rocky planets like Earth. Without the intense heat and pressure of a star's core, these elements wouldn't exist. But it's not just about the elements themselves, it's also about how they're distributed. Stellar winds, the streams of charged particles ejected by stars, play a crucial role in clearing away debris and shaping the environment where planets can form. Take our solar system as an example. Around 4.5 billion years ago, a cloud of gas and dust, enriched by the remnants of ancient stars, began to collapse under gravity. As it contracted, it formed a swirling disk of material around the young sun. Within this disk, tiny particles of dust, rich in heavy elements, clumped together, growing larger and larger until they formed the planets, moons, and asteroids we see today. The rocky inner planets, including Earth, owe their existence to the heavy elements forged in the hearts of stars that lived and died long before the sun was born. But the role of stellar remnants doesn't stop at creating rocky worlds. The elements scattered by dying stars also contribute to the diversity of planetary systems. In our own solar system, the distribution of elements shape the characteristics of each planet. Earth, for instance, has a core rich in iron and nickel, elements created in the cores of massive stars and scattered by supernova. Without these materials, our planet wouldn't have the magnetic field that protects us from harmful solar radiation, or the geological activity that drives plate tectonics and creates the conditions for life. As we look beyond our solar system, we see this process playing out across the universe. Planets orbiting other stars, known as exoplanets, show a stunning variety of compositions and environments, all shaped by the remnants of their local stellar ancestors. Some are gas giants, rich in hydrogen and helium, while others are rocky worlds like Earth, teeming with the heavy elements necessary for complex chemistry. This connection between stellar death and planetary birth raises an intriguing question. Could life arise from the ashes of stars? On Earth, the answer is a resounding yes. The carbon in our DNA, the oxygen we breathe, and the calcium in our bones all trace their origins back to the cores of ancient stars. In a very real sense, we are the products of stellar metamorphosis, living proof that the universe has the ability to transform destruction into creation and death into life. As we continue to explore the cosmos, we'll uncover even more about how the remnants of stars shape the universe, from the formation of planets to the potential for life beyond Earth. But for now, let's take a moment to appreciate the profound interconnectedness of it all, how the death of stars gives rise to worlds, and how those worlds, in turn, become the stage for new possibilities. This is the cycle of stellar metamorphosis, a story of transformation that reminds us of the beauty and resilience of the universe. In the vast tapestry of the cosmos, the search for exoplanets, planets orbiting stars beyond our solar system, has revolutionized our understanding of the universe. But what about planets that orbit the remnants of stars? These dying stars, white dwarfs, neutron stars, and other stellar remnants, offer a unique and often overlooked frontier in the hunt for new worlds. This is the next chapter in the story of stellar metamorphosis, the search for exoplanets around dying stars, and the extraordinary possibilities they hold. White dwarfs, the dense cores left behind by stars like our Sun, might seem like unlikely hosts for planets. After all, these stellar remnants are small, dim, and incredibly dense. Yet, recent discoveries have revealed that planets can not only survive the violent death of their parent star, but also thrive in its aftermath. Imagine a world orbiting a white dwarf, bathed in the faint glow of a cooling ember. While the star itself has faded, its gravitational pull remains strong enough to hold onto its planetary companions. These worlds, often forged from the ashes of their star's explosive past, could offer clues about the resilience of planetary systems in the face of stellar death. Neutron stars, the ultra-dense remnants of massive stars, present an even more intriguing possibility. PSRB 1257 plus 12, the first known exoplanet system, orbits a pulsar, a rapidly spinning neutron star. Discovered in the early 1990s, this system shattered the notion that planets could only form around main sequence stars. The planets here are unlike anything in our solar system, shaped by the extreme environment of their pulsar host. Could such worlds, constantly bombarded by intense radiation, ever support life? While the conditions seem hostile, the discovery of these planets has opened our minds to the incredible diversity of planetary systems in the universe. Detecting planets around stellar remnants is no easy task. White dwarfs, for example, emit very little light, making it difficult to spot orbiting planets using traditional methods like the transit technique, which relies on observing dips in a star's brightness as a planet passes in front of it. Neutron stars, on the other hand, are so small and dense that their planets must be detected indirectly, often by measuring tiny variations in the timing of the pulsar's radio pulses. These challenges have pushed astronomers to develop innovative techniques, from gravitational microlensing to advanced spectroscopy, all in the pursuit of uncovering these elusive worlds. What makes these discoveries so exciting is the potential for life. While planets orbiting white dwarfs or neutron stars face harsh conditions, they also offer unique opportunities. A planet orbiting a white dwarf, for instance, could find itself in a stable orbit within the star's habitable zone, the region where temperatures might allow liquid water to exist long after the star's death. Similarly, the intense radiation from a neutron star might create exotic forms of life, adapted to environments we can scarcely imagine. These possibilities remind us that life, in all its forms, is incredibly resilient, capable of thriving in even the most unexpected places. As we look to the future, the search for exoplanets around dying stars will continue to expand our understanding of the universe. Each discovery not only reveals new worlds, but also sheds light on the fate of planetary systems as their stars evolve. What happens to Earth-like planets when their stars become red giants? Can life persist on worlds orbiting stellar remnants? These questions drive astronomers forward, inspiring new missions and technologies to explore the cosmos. The story of stellar metamorphosis is far from over. As stars age, die, and transform, they leave behind a legacy that continues to shape the universe. From the birth of planets in the aftermath of supernova to the search for life on worlds orbiting white dwarfs and neutron stars, the cycle of creation and renewal unfolds on a cosmic scale. And as we peer deeper into the cosmos, we're reminded that the universe is not just a place of stars and galaxies. It's a living, evolving system, where even the end of one story can spark the beginning of countless others. The sun, our steadfast source of light, warmth, and life, has been a constant presence for billions of years, but like all stars, it too has a finite lifespan, and its future holds dramatic changes that will reshape the solar system as we know it. This is the story of our sun's inevitable transformation, a journey that mirrors the broader cosmic dance of stellar metamorphosis. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core, marking the beginning of the end for its current phase of life. As the core contracts under gravity, the outer layers will expand, swelling the sun into a red giant. During this phase, it will grow hundreds of times larger, engulfing the inner planets Mercury, Venus, and likely Earth. Imagine a star so vast that its outer layers stretch beyond Earth's orbit, its surface glowing with a deep red hue. This is the fate of our sun, a transformation that will fundamentally alter the solar system. For Earth, the consequences are profound. As the sun expands, its increasing brightness will scorch our planet long before it's engulfed. Oceans will evaporate, atmospheres will be stripped away, and the surface will become a barren, molten wasteland. Yet, even as the inner planets face destruction, the outer solar system may experience a temporary renaissance. The sun's expansion will warm the icy moons of Jupiter and Saturn, potentially creating environments where liquid water could exist, at least for a time. After its red giant phase, the sun will shed its outer layers, leaving behind a glowing core that will cool and dim into a white dwarf. This dense remnant, no larger than Earth but with half the mass of the original sun, will radiate faintly for trillions of years, a quiet ember in the vastness of space. Around it, a planetary nebula, a shimmering cloud of gas and dust will form, a final testament to the sun's once brilliant life. The transformation of the sun is a powerful reminder of the universality of stellar metamorphosis. Just as our star will evolve, so too will countless others across the cosmos. Some will follow a similar path, swelling into red giants before fading into white dwarfs. Others, more massive than the sun, will meet their ends in spectacular supernova, scattering their remains across the galaxy and seeding the universe with the elements needed for new stars and planets. This connection between our sun and other stars underscores the interconnectedness of the universe. Every star, no matter how distant or different, shares the same fundamental fate: to live, evolve, and eventually die, leaving behind a legacy that shapes the cosmos. And while the sun's future may seem distant, it's a vivid illustration of the processes that drive the universe's evolution. As we reflect on the fate of our sun, we're reminded of the delicate balance that sustains life on Earth and the impermanence of even the most familiar cosmic fixtures. But this isn't a story of loss, it's one of transformation. The death of stars, including our own, is a necessary part of the cosmic cycle, a process that ensures the universe remains vibrant and ever-changing. Looking beyond our solar system, we see that the sun's story is just one among countless others. Each star, in its own way, contributes to the grand tapestry of the cosmos, its life and death weaving together the threads of creation and destruction. And as we continue to explore the universe, we gain not only a deeper understanding of these processes, but also a greater appreciation for the beauty and resilience of the cosmos. The sun's journey is a microcosm of the universe itself, a reminder of the forces that shape our existence and the legacy we carry forward. From its fiery birth to its quiet end, the sun's story is a testament to the enduring cycle of stellar metamorphosis, a process that connects us all to the stars. As we've explored the life cycles of stars, one thing becomes clear: not all stellar deaths are created equal. The fate of a star is as unique as its fingerprint, shaped by its mass, composition, and the cosmic environment around it. While some stars fade quietly into the night, others go out in spectacular fashion, leaving behind a legacy of light and energy that defies imagination. This is the breathtaking diversity of stellar deaths, a cosmic tapestry woven with threads of beauty, chaos, and unpredictability. Take, for example, the hypernova. This rare and extreme event occurs when an exceptionally massive star collapses at the end of its life. Unlike a typical supernova, a hypernova releases an unimaginable amount of energy, often accompanied by a gamma-ray burst, a beam of intense radiation that can outshine entire galaxies for a brief moment. These bursts are so powerful that, if one were to occur nearby, it could strip Earth's atmosphere and devastate life as we know it. Yet, despite their destructive potential, hypernovae play a crucial role in the universe, scattering heavy elements and seeding the cosmos with the raw materials for new stars and planets. Another fascinating phenomenon is the pair instability supernova. These explosions occur in stars with masses between 100 and 200 times that of our Sun. In these stars, the core becomes so hot that it begins to produce pairs of electrons and positrons, reducing the pressure that supports the star against gravity. The result is a runaway collapse, followed by a cataclysmic explosion that obliterates the star entirely, leaving no remnant behind. Pair instability supernova are thought to have been more common in the early universe, when massive stars were more prevalent, and their explosive deaths may have played a key role in shaping the cosmos during its infancy. Then there are stars like Eta Carinae, a massive binary system that defies easy classification. This star, located in the Carina Nebula, has been on the brink of destruction for centuries. In the mid-19th century, it underwent a massive outburst, ejecting material equivalent to 10 times the mass of our Sun. Today, it remains unstable, a ticking time bomb that could explode as a hypernova or even collapse into a black hole. Eta Carinae serves as a reminder that stellar evolution is far from predictable. A star's fate can change in an instant, driven by forces we're only beginning to understand. These rare and dramatic events underscore the sheer variety of ways stars can die, from the quiet fading of red dwarfs to the explosive fury of hypernova. Each stellar death is a unique chapter in the story of the universe. And while these events may seem chaotic, they're also deeply beautiful, a testament to the universe's capacity for both destruction and creation. As we reflect on the diversity of stellar deaths, we're reminded of the delicate balance that governs the cosmos. Stars may live for billions of years, but their deaths are often fleeting, a brief flash of light against the vast backdrop of space. Yet in that fleeting moment, they leave an indelible mark, shaping the universe in ways that resonate for eons. Whether it's the gentle glow of a planetary nebula or the blinding brilliance of a gamma-ray burst, each stellar death contributes to the ongoing story of the cosmos, a story that continues to unfold with every passing moment. As we move forward, let's consider how these explosive events shape the universe on a larger scale. From the birth of new stars to the formation of galaxies, the death of one star can spark the creation of countless others, weaving a tapestry of light and life that stretches across the cosmos. These are the echoes of stellar metamorphosis, a reminder that even in death, stars continue to inspire and transform the universe around them. Among the many mysteries of the universe, few are as puzzling or as pervasive as dark matter. This invisible substance makes up about 85% of all matter in the cosmos, yet it doesn't interact with light or other forms of electromagnetic radiation. It's a cosmic ghost, detectable only through its gravitational effects on galaxies and clusters of galaxies. But what role does dark matter play in the life and death of stars? Could this enigmatic force be shaping the very processes of stellar metamorphosis? One of the most intriguing theories suggests that dark matter might influence star formation. Imagine a vast, invisible web stretching across the universe, its threads made of dark matter. These filaments act as cosmic scaffolding, guiding the flow of gas and dust into dense regions where stars can form. Without dark matter, galaxies might not have enough mass to hold together, and the conditions for star birth could be far less favorable. In this way, dark matter might be the hidden architect of stellar nurseries, silently shaping the environments where stars ignite. Once stars are born, dark matter could continue to play a role in their evolution. Some researchers hypothesize that dark matter particles, if they exist within stars, could alter the way energy is transported from the core to the surface. For example, in low-mass stars like red dwarfs, dark matter might slow down the fusion process, extending their already impressive lifespans. In more massive stars, it could affect the stability of the core, potentially delaying or accelerating their transformation into red giants or supernova. While these ideas remain speculative, they open up fascinating possibilities for how dark matter might subtly influence the life cycles of stars. But the impact of dark matter doesn't stop there. When stars die, their remnants, white dwarfs, neutron stars, and black holes, could also interact with dark matter in unexpected ways. Neutron stars, with their incredibly dense cores, might act as natural traps for dark matter particles, accumulating them over time and altering their internal dynamics. Black holes, the ultimate endpoints for massive stars, could even be surrounded by halos of dark matter, adding to their gravitational influence and shaping the way they interact with their surroundings. To understand dark matter, think of it as a cosmic conductor, orchestrating the movements of galaxies and stars without ever stepping into the spotlight. Its presence is felt everywhere, from the largest structures in the universe to the smallest processes within stars. Yet, despite its ubiquity, dark matter remains one of the greatest unsolved mysteries in modern science. As we consider the role of dark matter in stellar evolution, we're reminded of how much we still have to learn about the forces that shape the universe. From its potential influence on star formation to its mysterious interactions with stellar remnants, dark matter challenges our understanding and invites us to explore new frontiers. But dark matter isn't the only mysterious force at play in the cosmos. As we continue our journey through the life cycles of stars, let's turn our attention to another enigmatic phenomenon: dark energy. This mysterious force, driving the accelerated expansion of the universe, could be shaping the fate of stars and galaxies in ways we're only beginning to comprehend. Together, these invisible forces remind us that the universe is far more complex and far more wondrous than we can yet imagine. Stellar winds and radiation, these are the unseen forces that stars wield to sculpt their surroundings, shaping the very fabric of the cosmos. Picture a star not just as a glowing orb in space, but as a dynamic engine, constantly emitting streams of charged particles and intense light. These stellar winds and radiation don't just vanish into the void, they interact with the gas and dust around them, carving out vast regions of space and triggering new cycles of creation. Take the Orion Nebula, one of the most famous stellar nurseries in the night sky. Located about 1,300 light-years from Earth, this glowing cloud of gas and dust is a hotbed of star formation. But what's truly fascinating is how the stars within it are shaping their own environment. The massive young stars at the heart of the nebula, known as the trapezium cluster, blast out powerful stellar winds and ultraviolet radiation. These forces push the surrounding gas and dust outward, clearing away material and creating cavities within the nebula. This process isn't just destructive, it's also creative. As the stellar winds and radiation sweep through the nebula, they compress the gas and dust in their path, triggering the collapse of denser regions. These collapsing clouds, in turn, give birth to new stars. It's a cosmic feedback loop where the death of one star's environment becomes the cradle for another. The Orion Nebula is a perfect example of this interplay, a place where the life cycles of stars are intimately connected to the evolution of their surroundings. But the influence of stellar winds and radiation doesn't stop at star formation. These forces also play a crucial role in shaping planetary systems. When a star is young, its intense radiation can strip away the atmospheres of nearby planets, leaving behind barren, rocky worlds. On the other hand, stellar winds can push gas and dust outward, creating the conditions for icy bodies and gas giants to form in the outer reaches of a planetary system. Consider our own solar system. The sun's early winds and radiation likely played a key role in clearing out the inner solar system, allowing rocky planets like Earth to form. At the same time, these forces helped shape the outer solar system, where gas giants like Jupiter and Saturn took shape amid the remnants of the sun's formative years. The impact of stellar winds and radiation extends even further, influencing the atmospheres of planets long after their formation. For example, the solar wind, a stream of charged particles from the sun, constantly interacts with Earth's magnetic field, creating phenomena like the auroras. On planets without protective magnetic fields, however, stellar winds can erode atmospheres over time, leaving behind desolate landscapes. This interplay between stars and their environments is a reminder of the universe's interconnectedness. From the birth of stars in nebulae to the evolution of planetary systems, stellar winds and radiation are the invisible hands that guide the cosmos. They are the forces that transform chaos into order, destruction into creation, and darkness into light. As we look deeper into the cosmos, we begin to see how these processes shape not just individual stars and planets, but entire galaxies. The winds and radiation from countless stars work together, driving the evolution of galaxies and seeding the universe with the building blocks of life. It's a story of transformation, one that reminds us of the incredible forces at play in the universe and the delicate balance that makes it all possible. Now, let's turn our attention to how these forces extend beyond individual stars, influencing the large-scale structure of the universe itself. From the birth of galaxies to the evolution of cosmic ecosystems, the legacy of stellar winds and radiation continues to shape the cosmos in ways that are as profound as they are beautiful. In the vast expanse of the cosmos, stars rarely exist in isolation. Many are born in pairs or even groups, gravitationally bound to one another in a celestial dance that can last billions of years. These binary and multiple star systems add a layer of complexity to the life cycles of stars, creating scenarios that are as fascinating as they are unpredictable. From dramatic mass transfers to explosive mergers, the interactions between stars in these systems can lead to extraordinary outcomes, shaping the universe in ways that single stars never could. Take Sirius, the brightest star in our night sky. What appears to be a single point of light is actually a binary system consisting of Sirius A, a main sequence star, and Sirius B, a white dwarf. These two stars orbit each other every 50 years, locked in a gravitational embrace that has shaped their evolution. Sirius B, once a massive star, has already gone through its red giant phase, shedding its outer layers and leaving behind a dense remnant. Its companion, Sirius A, continues to shine brightly, but the presence of Sirius B has undoubtedly influenced its journey. This interplay between stars, where one's death can alter the life of another, is a hallmark of binary systems, showcasing the intricate relationships that define them. But the story doesn't end there. In some binary systems, the stars are so close together that they begin to exchange material. This process, known as mass transfer, occurs when one star expands into a red giant and its outer layers spill over onto its companion. The result can be a dramatic transformation for both stars. The donor star, stripped of its outer layers, may collapse into a white dwarf or neutron star, while the recipient star, now enriched with new material, could evolve into a blue giant or even explode as a supernova. One of the most dramatic outcomes of mass transfer is the formation of exotic objects like Thorne-Zitkow objects. These rare hybrids occur when a neutron star is engulfed by a red giant, creating a star within a star. The neutron star orbits within the red giant's outer layers, its intense gravity pulling material from its companion and altering the star's internal structure. While Thorne-Zitkow objects remain theoretical, their potential existence highlights the incredible diversity of stellar relationships and the surprising outcomes that can arise from binary interactions. Then there are systems like Cygnus X1, a binary pair consisting of a massive blue supergiant and a black hole. In this case, the black hole's immense gravity pulls material from its companion, creating a swirling disk of gas that emits powerful X-rays. This process, known as accretion, not only fuels the black hole, but also produces some of the most energetic phenomena in the universe. Cygnus X1 serves as a vivid reminder of how binary systems can give rise to some of the most extreme and mysterious objects in the cosmos. The complexity of binary and multiple star systems is a testament to the dynamic nature of the universe. These stellar relationships, shaped by gravity, mass transfer, and sometimes violent interactions, remind us that stars are not solitary actors but interconnected players in a grand cosmic drama. Their stories are intertwined, their fates linked, and their legacies forever bound together. As we reflect on the intricate dance of binary stars, we begin to see the universe as a place of endless connections, where the actions of one star can ripple through space and time, shaping the lives of others. From the quiet companionship of Sirius to the explosive power of Cygnus X1, binary systems offer a window into the profound relationships that define the cosmos. And as we continue to explore these systems, we uncover not just the secrets of stars, but the deeper truths about how the universe itself evolves. Looking ahead, let's consider how these complex stellar relationships extend beyond binary systems, influencing the formation of galaxies, the distribution of elements, and even the potential for life. The universe, it seems, is a place where no star is truly alone, and where every connection tells a story. Magnetic fields, those invisible lines of force that shape so much of our universe, are not just confined to Earth or the magnets on your fridge. They play a crucial role in the life and death of stars, influencing everything from their fiery surfaces to their explosive ends. These fields are like cosmic fingerprints, unique to each star, and they leave their mark on every stage of stellar evolution. But how exactly do magnetic fields shape the lives of stars, and what happens when they become incredibly strong? Let's start with our own sun. Its magnetic field is a dynamic, ever-changing force, cycling through periods of high and low activity in what's known as the solar cycle. During periods of high activity, the sun's magnetic field becomes tangled and twisted, leading to sunspots, solar flares, and coronal mass ejections. These eruptions send streams of charged particles hurtling through space, creating the stunning auroras we see on Earth and influencing the behavior of planets throughout the solar system. But the Sun's magnetic field doesn't just affect its surroundings, it also shapes the star itself. The interplay between magnetic forces and the Sun's turbulent outer layers drives solar winds, the streams of charged particles that flow outward into space, sculpting the heliosphere and defining the boundaries of our solar system. Now, imagine a star much more massive than the Sun, with a magnetic field thousands or even millions of times stronger. Such stars exist, and their magnetic fields can dramatically alter their evolution. For example, magnetic fields can channel and accelerate stellar winds, stripping away a star's outer layers at a faster rate. This process not only shortens the star's lifespan, but also enriches the surrounding space with heavy elements, seeding the cosmos with the building blocks for future stars and planets. When massive stars reach the end of their lives, their magnetic fields can become even more extreme. As the core collapses during a supernova, the star's magnetic field is compressed and amplified, creating some of the most powerful magnetic fields in the universe. Neutron stars, the dense remnants of these explosions, often inherit these intense fields. Some neutron stars, known as magnetars, have magnetic fields so strong they can distort the structure of atoms and even affect the fabric of space-time itself. These cosmic powerhouses emit bursts of X-rays and gamma rays, lighting up the universe with their magnetic fury. The impact of magnetic fields doesn't stop there. They also influence the formation of planetary systems around young stars. Magnetic fields can regulate the flow of gas and dust in protoplanetary disks, guiding the formation of planets and shaping their orbits. Without these fields, the chaotic environment of a young star system might never settle into the orderly arrangement of planets we see today. As we explore the role of magnetic fields in stellar evolution, we begin to see how deeply interconnected the forces of the universe are. From the gentle solar winds of our Sun to the explosive power of magnetars, magnetic fields shape the lives of stars in ways that are both subtle and profound. They remind us that the universe is not just a place of light and gravity, but also one of invisible forces that guide its evolution. But magnetic fields are just one piece of the puzzle. As we continue our journey through the cosmos, let's turn our attention to other forces that shape stellar metamorphosis, forces that, like magnetic fields, are unseen but no less powerful. Together, these forces weave the intricate tapestry of the universe, creating the stars, planets, and galaxies that fill the night sky with wonder. As we delve deeper into the lives of stars, we encounter a phenomenon that adds a layer of unpredictability to their evolution: cosmic collisions. Imagine two stars, each following their own path through the galaxy, suddenly crossing trajectories in a violent encounter. These collisions, while rare, can dramatically alter the fate of stars, reshaping their life cycles and leaving behind extraordinary remnants. From the creation of bizarre stellar hybrids to the disruption of entire planetary systems, cosmic collisions remind us that the universe is a dynamic and sometimes chaotic place. One of the most fascinating results of stellar collisions is the formation of blue stragglers. These stars, found in dense star clusters, appear younger and hotter than their neighbors, defying the expectations of stellar evolution. How do they form? When two stars collide and merge, their combined mass reignites nuclear fusion in the core, creating a star that shines brighter and bluer than before. Blue stragglers are a testament to the transformative power of cosmic encounters, proving that even in the vastness of space, stars can collide and create something entirely new. But the effects of these collisions aren't limited to the stars themselves. Planetary systems orbiting these stars can be thrown into chaos. Picture a star with a family of planets, each following a stable orbit, suddenly disrupted by the gravitational pull of a passing star. The result can be catastrophic: planets flung into the void of space or drawn into unstable, erratic orbits. In some cases, the collision itself can destroy planets, reducing them to dust and gas. These disruptions remind us that the stability of planetary systems is fragile, constantly at the mercy of the cosmos's unpredictable forces. Then there are hypervelocity stars, stellar outliers that have been ejected from their home galaxies at incredible speeds. These stars are often the result of close encounters with supermassive black holes, whose immense gravity can slingshot stars into intergalactic space at millions of miles per hour. Imagine a star, once part of a bustling galaxy, now hurtling through the void, its light a solitary beacon in the darkness. Hypervelocity stars are a vivid reminder of the power of cosmic collisions, capable of altering not just individual stars but the very fabric of galaxies. A striking example of these collisions can be seen in NGC 7252, a galaxy sometimes called the Atoms for Peace galaxy due to its peculiar structure. Here, two galaxies have collided, their stars and gas swirling together in a cosmic dance. Within this chaos, new stars are born and old ones are reshaped, creating a tapestry of stellar evolution that spans millions of years. NGC 7252 is a living laboratory, offering astronomers a glimpse into the transformative effects of galactic collisions. The broader implications of these encounters are profound. Cosmic collisions not only alter the lives of stars, but also influence the evolution of galaxies and the distribution of elements throughout the universe. They remind us that the cosmos is a place of constant interaction, where even the most distant objects can shape one another's destinies. As we consider the role of cosmic collisions, we begin to see the universe as a web of connections, where every star, every planet, and every galaxy is part of a larger, ever-evolving story. These encounters, while rare, are a testament to the dynamic nature of the cosmos, a place where destruction and creation are two sides of the same cosmic coin. Looking ahead, let's explore how these interactions extend beyond individual stars and galaxies, shaping the large-scale structure of the universe itself. From the birth of new stars in the wake of collisions to the distribution of heavy elements across the cosmos, the legacy of these encounters continues to shape the universe in ways that are as profound as they are beautiful. At the heart of nearly every galaxy, including our own Milky Way, lies a supermassive black hole, a cosmic giant with a gravitational pull so immense it can shape the fate of entire star systems. These colossal objects, millions or even billions of times more massive than our Sun, are not just passive observers of the universe. They are active participants in the life and death of stars. From tearing apart stars that venture too close to fueling some of the brightest objects in the cosmos, supermassive black holes play a pivotal role in the ongoing drama of stellar evolution. One of the most dramatic interactions between stars and supermassive black holes is a tidal disruption event. Imagine a star minding its own business in the vast expanse of space, wandering too close to a black hole's event horizon. As it approaches, the black hole's immense gravity begins to stretch and pull the star apart, a process known as spaghettification. The star is torn into a stream of gas, spiraling into the black hole and releasing an incredible burst of energy. These events, while rare, can outshine entire galaxies for weeks, offering astronomers a fleeting yet spectacular glimpse into the destructive power of supermassive black holes. But it's not just destruction. Supermassive black holes also play a creative role in the cosmos. As stars and other materials spiral into these black holes, they form an accretion disk, a swirling ring of superheated gas and dust. This disk can glow with incredible brightness, often outshining all the stars in the galaxy combined. In some cases, the energy released by these disks can even trigger the formation of new stars in the surrounding regions, creating a feedback loop where the death of one star fuels the birth of many others. Take Sagittarius A, the supermassive black hole at the center of our Milky Way. While it's relatively quiet compared to others, it still exerts a profound influence on its surroundings. Stars in its vicinity orbit at incredible speeds, their paths shaped by the black hole's gravity. Occasionally, these stars come perilously close, risking a tidal disruption event. Even when they don't, their interactions with Sagittarius provide valuable insights into the behavior of black holes and the forces that govern galactic centers. The role of supermassive black holes extends beyond their immediate vicinity. Their gravitational influence can shape the structure of entire galaxies, guiding the motion of stars and gas on a grand scale. In some galaxies, the energy emitted by supermassive black holes can even halt star formation by heating up the surrounding gas, preventing it from collapsing into new stars. This delicate balance between creation and destruction is a testament to the interconnectedness of cosmic phenomena, where the actions of one object can ripple across an entire galaxy. Reflecting on these processes, we see a universe that is deeply intertwined, from the birth of stars in nebulae to their explosive deaths near supermassive black holes. Every event is part of a larger cosmic tapestry. The forces that shape stars are the same forces that shape galaxies, and the remnants of one star's death can become the seeds of another's birth. It's a reminder that the universe is not just a collection of isolated objects, but a dynamic, interconnected system where every action has a reaction. As we continue to explore the cosmos, we uncover more about how these massive black holes influence the life cycles of stars and the evolution of galaxies. Their presence, while often hidden, is felt everywhere, shaping the universe in ways that are both profound and beautiful. And as we peer deeper into the night sky, we're reminded that even in the darkest corners of space, there is light, energy, and the potential for new beginnings. Now, let's turn our gaze beyond individual galaxies to explore how these supermassive black holes, along with other cosmic forces, shape the large-scale structure of the universe itself. From the birth of galaxy clusters to the distribution of matter across the cosmos, the legacy of these cosmic giants continues to unfold, revealing a universe that is as interconnected as it is infinite. Imagine peering into the night sky and seeing not just the stars of today, but the ancient remnants of the universe's earliest days. This is the essence of stellar archaeology, a fascinating field that uses the light from ancient stars to uncover the secrets of the cosmos's infancy. These stars, often referred to as stellar fossils, are like celestial time capsules, preserving the chemical fingerprints of the universe's first generations of stars. By studying them, astronomers can piece together the story of how the universe evolved from its chaotic beginnings to the structured cosmos we see today. One of the most remarkable examples of a stellar fossil is He 152309001, a star located in the halo of the Milky Way. This ancient star is estimated to be over 13 billion years old, making it one of the oldest stars ever discovered. Its composition is strikingly different from younger stars like our Sun. He-152309001 contains very few heavy elements, just a fraction of what's found in the Sun. This lack of heavy elements, or metallicity, is a key clue to its origins. Unlike newer stars, which formed from gas enriched by previous stellar generations, He-152309001 was born from material that had barely been touched by the nuclear furnaces of earlier stars. The study of stars like He-152309001 offers a unique window into the early universe. These ancient stars formed during a time when the cosmos was still in its infancy, just a few 100 million years after the Big Bang. The first stars, known as population 3 stars, were massive and short-lived, exploding as supernova and scattering their elements into the surrounding gas. This enriched material became the building blocks for the next generation of stars, including the stellar fossils we observe today. By analyzing their chemical makeup, astronomers can infer the properties of those first stars, even though none have been directly observed. But why does this matter? Stellar archaeology isn't just about satisfying our curiosity. It's about understanding the origins of everything around us. The heavy elements forged in the hearts of those first stars are the same elements that make up planets, life, and even our own bodies. By studying stellar fossils, we're essentially tracing our cosmic ancestry, uncovering the processes that shaped the universe and made life possible. The legacy of these ancient stars lives on in modern stars as well. While stars like He-152309001 are rare, their influence is woven into the fabric of the cosmos. Every star born today carries a trace of those early generations, their chemical signatures blending with the enriched material of countless supernovae. This interconnectedness reminds us that the universe is a tapestry, woven together by the lives and deaths of stars across billions of years. As we continue to explore the cosmos, stellar archaeology offers a unique perspective on the universe's history. By studying these ancient stars, we're not just looking back in time, we're uncovering the foundations of the universe itself. And as we turn our gaze to the stars of today, we're reminded that they, too, carry the echoes of their ancestors, a testament to the enduring legacy of stellar metamorphosis. Now, let's shift our focus to how these ancient stars and their modern descendants continue to shape the universe, from the formation of galaxies to the potential for life on distant worlds. The story of stellar fossils is far from over. It's a thread that connects the past, present, and future of the cosmos. The universe isn't just a vast expanse of stars and galaxies. It's a cosmic laboratory where the life and death of stars forge the very elements that make up everything around us. This process, known as nucleosynthesis, is the heart of cosmic chemistry, transforming the simplest elements into the building blocks of planets, life, and even the stars themselves. From the hydrogen and helium born in the Big Bang to the carbon in our DNA and the iron in our blood, every element has a stellar origin story. Let's start with the basics. In the early universe, only the lightest elements, hydrogen and helium, existed. These elements were created in the fiery moments following the Big Bang, but they were just the beginning. The heavier elements, the ones essential for life and the diversity of the cosmos, had to be forged in the hearts of stars. This is where stellar metamorphosis plays its most critical role. Inside a star's core, the intense heat and pressure create the perfect conditions for nuclear fusion. hydrogen atoms collide and fuse into helium, releasing energy that powers the star. But as stars age and exhaust their hydrogen fuel, they begin to fuse heavier elements. Helium fuses into carbon, carbon into oxygen, and so on, up to iron. Each fusion reaction releases energy and creates new elements, enriching the star's core with a mix of heavier atoms. When stars die, they scatter these elements into space, seeding the cosmos with the raw materials for new stars, planets, and even life. For smaller stars, this happens gently through the formation of planetary nebulae. The outer layers drift away, leaving behind a white dwarf and a glowing cloud of gas rich in carbon, nitrogen, and oxygen. For massive stars, the process is far more dramatic. In a supernova explosion, the star's core collapses, and the outer layers are blasted into space, carrying with them a wealth of heavy elements like gold, silver, and uranium. These stellar remnants don't just vanish, they become part of the interstellar medium, the vast clouds of gas and dust that fill the space between stars. Over time, these clouds collapse under gravity, forming new stars and planets. Our solar system, for example, formed from a cloud enriched by the remnants of ancient stars. Every atom of carbon in your body, every molecule of oxygen in the air you breathe, was forged in the heart of a star that lived and died billions of years ago. This cosmic recycling process is a testament to the interconnectedness of the universe. The death of one star becomes the birth of countless others, each carrying the legacy of its ancestors. It's a cycle that has been repeating for over 13 billion years, shaping the evolution of galaxies, the formation of planets, and the emergence of life. But nucleosynthesis doesn't just create the elements, it also influences the structure and chemistry of the cosmos. The distribution of elements affects how stars form, how galaxies evolve, and even how planets develop. For instance, the presence of heavy elements like carbon and oxygen in a star system increases the likelihood of rocky planets forming, creating environments where life could potentially arise. Reflecting on this process, we see a universe that is not just vast and beautiful, but deeply interconnected. The life and death of stars are not isolated events, they are part of a grand, cosmic cycle that shapes everything from the smallest atom to the largest galaxy. And as we continue to explore the cosmos, we're reminded that the story of stellar metamorphosis is also our story, written in the elements that make up our world and ourselves. Now, let's turn our attention to how these processes extend beyond individual stars, influencing the large-scale structure of the universe and the potential for life across the cosmos. The legacy of stellar metamorphosis is far-reaching, shaping not just the chemistry of the universe, but its very destiny. The study of stellar evolution is entering an era of unprecedented discovery, driven by cutting-edge technology and groundbreaking theories that are reshaping our understanding of the cosmos. At the forefront of this revolution is the James Webb Space Telescope, a marvel of engineering that peers deeper into space and further back in time than ever before. With its infrared vision, Webb can pierce through cosmic dust, revealing the hidden details of star formation in distant galaxies and shedding light on the earliest stages of stellar metamorphosis. This powerful tool is already transforming our understanding of how stars are born, live, and die, offering glimpses into processes that were once shrouded in mystery. But it's not just about observing the universe, it's also about simulating it. Advances in computational modeling are allowing scientists to recreate the complex physics of stars with astonishing precision. These virtual laboratories let researchers explore scenarios that are impossible to observe directly, from the inner workings of a supernova to the chaotic collisions of binary stars. By combining observational data with these simulations, astronomers can test theories, refine models, and uncover hidden patterns in the life cycles of stars. One of the most exciting areas of research is the study of stellar remnants. Neutron stars, black holes, and white dwarfs are no longer just theoretical curiosities. They're windows into the extremes of physics. With instruments like gravitational wave detectors, we can now listen to the universe, capturing the ripples in space-time caused by collisions between neutron stars and black holes. These observations are revealing new details about the behavior of matter under conditions that defy imagination, from the crushing densities of neutron stars to the warped space-time around black holes. The future of stellar evolution studies also holds promise for uncovering the origins of life itself. By analyzing the chemical fingerprints of ancient stars, astronomers are piecing together the history of cosmic chemistry, tracing the journey of elements from the hearts of stars to the planets orbiting them. This research could answer fundamental questions about how the building blocks of life, like carbon and oxygen, became so abundant in the universe, and whether similar processes are at work in other star systems. As we stand on the brink of these discoveries, it's worth reflecting on the philosophical implications of our quest to understand stellar evolution. What does it mean to uncover the secrets of stars that lived and died billions of years before our sun ignited? In a sense, we are cosmic archaeologists, piecing together the story of the universe and our place within it. The study of stellar metamorphosis isn't just about understanding distant stars, it's about understanding ourselves, our origins, and the interconnectedness of all things. Looking ahead, the possibilities are as vast as the cosmos itself, from the next generation of space telescopes to the development of quantum computing. The tools at our disposal will only grow more powerful. Each new discovery will bring us closer to answering questions that have puzzled humanity for millennia. How did the universe begin? How do stars shape the cosmos? And what does it all mean for the future of life in the universe? The study of stellar evolution is more than a scientific endeavor. It's a journey of exploration and discovery, one that connects us to the stars and to each other. As we continue to explore the cosmos, we're not just uncovering the secrets of the universe, we're also uncovering the potential for new beginnings, new stories, and new wonders waiting to be revealed. The death of a star is not just a scientific event, it's a cosmic metaphor, a reminder of the profound cycles that govern both the universe and our own lives. In the vastness of space, stars are born, they shine, and they fade, each stage a testament to the beauty of impermanence. Just as a star's life is finite, so too is everything in nature, from the fleeting bloom of a flower to the rise and fall of civilizations. Yet within this impermanence lies a deeper truth, the promise of renewal. When a star dies, it doesn't vanish. It transforms, scattering its essence into the cosmos, where it becomes the building blocks for new stars, new worlds, and even new life. This cycle of creation and destruction is not unique to stars. It echoes throughout the natural world. Think of a forest fire, devastating in its power, yet essential for the regeneration of the ecosystem. Or consider the changing of the seasons, where the decay of autumn gives way to the rebirth of spring. These cycles remind us that death is not an end, but a transition, a necessary step in the ongoing dance of existence. In the same way, the death of a star is not a final act, but a beginning. Its remnants, whether a glowing planetary nebula or the explosive shockwaves of a supernova, become the seeds of future creation, weaving a tapestry of interconnectedness that spans the cosmos. There's a poetic symmetry in this process, a harmony that connects the smallest atoms to the largest galaxies. Every element forged in the heart of a star, the carbon in our bones, the iron in our blood, bears witness to this cosmic legacy. We are quite literally made of stardust, a living testament to the interconnectedness of all things. This realization invites us to see ourselves not as separate from the universe, but as an integral part of its story. The life and death of stars mirror our own journeys, reminding us that we, too, are part of a greater whole. Yet, while these philosophical reflections inspire awe, they also ground us in the reality of scientific exploration. The remnants of stellar deaths, white dwarfs, neutron stars, black holes, are not just poetic symbols, they are windows into the extremes of physics. By studying these remnants, we uncover the mechanisms that drive the universe, from the crushing densities of neutron stars to the warped space-time around black holes. Each discovery deepens our understanding of the cosmos, bridging the gap between the poetic and the practical. As we contemplate the philosophical implications of stellar death, we're reminded that science and wonder are not at odds. They are two sides of the same coin. The study of stars is not just about understanding the mechanics of the universe. It's about exploring the profound questions that have captivated humanity for millennia. What does it mean to be part of something so vast? How do we find meaning in the cycles of creation and destruction? And what can the stars teach us about our own place in the cosmos? Returning to the scientific lens, we see that the story of stellar remnants is far from over. Each observation, each discovery, adds a new layer to our understanding of how stars live, die, and transform. Whether it's the delicate glow of a planetary nebula or the violent aftermath of a supernova, these remnants are not just relics of the past, they are active participants in the ongoing evolution of the universe. And as we continue to explore their mysteries, we're reminded that the cosmos is not just a place of stars and galaxies, but a living, breathing system, where every end is also a beginning, and every death carries the promise of renewal. This interplay between the philosophical and the scientific enriches our understanding of the cosmos, inviting us to see the universe not just as a collection of objects, but as a story, one that we are all a part of. As we turn our gaze to the stars, we're not just observers, we're participants in a grand, unfolding narrative where the echoes of stellar death reverberate through time and space, shaping the destiny of everything within it. In the vast expanse of the cosmos, the study of stars isn't just reserved for professional astronomers in observatories with towering telescopes. It's a field that's being shaped by people from all walks of life, amateur astronomers, students, and even hobbyists with a passion for the night sky. This is the world of citizen science, where everyday stargazers contribute to groundbreaking discoveries, helping to unravel the mysteries of stellar metamorphosis. By harnessing the collective power of curious minds, citizen science is transforming how we explore the universe, proving that you don't need a PhD to make a difference in astrophysics. Take the Zooniverse platform, for example. This online hub brings together millions of volunteers from around the globe, inviting them to analyze real scientific data. Projects like Galaxy Zoo and Planet Hunters allow participants to classify galaxies, search for exoplanets, and even identify unusual stellar phenomena. It's a collaborative effort that has led to some remarkable discoveries. In one case, a Dutch schoolteacher named Hanny van Arkel spotted a strange, greenish object while classifying galaxies. This object, later named Hanny's voorwerp Dutch for Hany's object, turned out to be a rare quasar ionization echo, a discovery that professional astronomers might have missed without her keen eye. But it's not just about spotting unusual objects. Citizen scientists are also playing a crucial role in tracking the life cycles of stars. Projects like Supernova Hunters invite volunteers to sift through telescope data, searching for the telltale signs of stellar explosions. These efforts have led to the discovery of supernovae that might otherwise have gone unnoticed, providing valuable insights into how stars die and what they leave behind. The power of these discoveries lies in the sheer number of participants. What one person might miss, another will catch, creating a collective intelligence that rivals even the most advanced algorithms. The impact of citizen science goes beyond individual discoveries. It's also about democratizing space exploration, making it accessible to anyone with an internet connection and a sense of curiosity. This shift is empowering people to engage with science in a way that was once unimaginable, fostering a deeper appreciation for the cosmos and inspiring the next generation of astronomers. For many, it's not just about contributing to research, it's about being part of something larger, a global community united by a shared love of the stars. Technology has played a pivotal role in this transformation. With the rise of powerful telescopes, open data initiatives, and user-friendly platforms, the barriers to entry have never been lower. Amateur astronomers can now access high-quality images of the night sky, analyze data from professional observatories, and even control telescopes remotely. This democratization of tools is leveling the playing field, allowing anyone with a passion for the stars to contribute meaningfully to our understanding of the universe. The success of citizen science also highlights the importance of collaboration in scientific research. While professional astronomers bring expertise and advanced tools, citizen scientists bring fresh perspectives, diverse experiences, and an unparalleled enthusiasm for discovery. Together, they form a powerful partnership, one that is pushing the boundaries of what we know about stars, galaxies, and the cosmos as a whole. As we look to the future, the role of citizen science in stellar research is only set to grow. With new projects, tools, and technologies emerging all the time, the opportunities for discovery are limitless. Whether you're a seasoned stargazer or someone who's just starting to explore the night sky, there's a place for you in this cosmic journey. After all, the universe is vast, and its secrets are too big for any one person to uncover alone. This collaborative spirit isn't just changing how we study stars, it's changing how we see ourselves in the universe. By working together, we're not just uncovering the mysteries of stellar metamorphosis, we're building a deeper connection to the cosmos and to each other. And as we continue to explore, we're reminded that the stars belong to all of us, and their stories are ours to discover together. Now, let's turn our attention to how this democratization of space exploration is shaping the next frontier of stellar research, where technology and community are unlocking new possibilities for understanding the universe. As we continue our exploration of stellar metamorphosis, it's impossible to ignore the growing influence of artificial intelligence and machine learning. These cutting-edge technologies are revolutionizing how we study stars, turning the overwhelming flood of astronomical data into meaningful insights. With the universe producing more information than humans could ever process alone, AI has become an indispensable tool, helping us uncover patterns, predict stellar behavior, and even discover entirely new phenomena. One of the most striking examples of AI's impact is in the search for exoplanets. NASA's Kepler mission, for instance, collected data on hundreds of thousands of stars, each with its own unique light patterns. Sifting through this data manually would take lifetimes, but machine learning algorithms can analyze it in a fraction of the time. By training these algorithms to recognize the subtle dips in a star's brightness that indicate a passing planet, researchers have identified thousands of exoplanets, many of which might have otherwise gone unnoticed. This isn't just about finding new worlds, it's about redefining what's possible in astronomy. AI's role extends far beyond exoplanet discovery. It's also transforming how we study stellar evolution. For example, machine learning models can analyze the spectra of stars, their unique light signatures, to determine their composition, temperature, and age. This allows astronomers to classify stars more accurately and track their life cycles with unprecedented precision. In some cases, AI has even identified anomalies that led to the discovery of entirely new types of stars or unexpected stellar phenomena. But AI isn't just a tool for discovery, it's also a predictor. By analyzing vast datasets of stellar behavior, machine learning algorithms can forecast how stars will evolve, when they might explode as supernova, or how their magnetic fields might change over time. These predictions aren't just theoretical, they're helping astronomers plan observations, prioritize research, and even prepare for rare cosmic events. In a field where timing is everything, AI is proving to be an invaluable ally. Of course, the rise of AI in astronomy isn't without its challenges. As we rely more on these technologies, ethical questions arise. How do we ensure that AI-driven discoveries are transparent and reproducible? What happens when algorithms make decisions that human researchers don't fully understand? And as AI becomes more integrated into the scientific process, how do we balance its capabilities with the intuition and creativity of human astronomers? These are complex issues, but they're essential to address as we move forward. The integration of AI into stellar studies is a testament to the power of collaboration, not just between humans and machines, but across disciplines. By combining the strengths of astrophysics, computer science, and data analysis, we're pushing the boundaries of what we can achieve. From uncovering hidden worlds to predicting the fates of stars, AI is helping us see the universe in ways we never could before. As we reflect on the role of AI in astronomy, it's clear that this is just the beginning. With each new algorithm, each new dataset, we're unlocking new possibilities for understanding the cosmos. But as we embrace these tools, we must also remain mindful of their limitations and ethical implications. After all, the goal isn't just to use AI to study the stars, it's to ensure that these technologies serve humanity's broader quest for knowledge and discovery. Now, let's turn our gaze to the broader implications of these technological advancements, exploring how they're shaping the future of astronomy and our understanding of the universe. The story of stellar metamorphosis is far from over, and with AI as our guide, the possibilities are as vast as the cosmos itself. As we marvel at the wonders of stellar metamorphosis, the birth, life, and death of stars, we're also faced with profound ethical questions that go beyond the science itself. How do we ensure that our exploration of the cosmos benefits all of humanity, rather than a select few? And as we push the boundaries of space technology, how do we navigate the fine line between discovery and exploitation? These are the ethical considerations that come with studying the stars, and they remind us that our relationship with the universe is as much about responsibility as it is about curiosity. One of the most pressing issues is the allocation of resources. Space exploration is undeniably expensive, requiring billions of dollars in funding for telescopes, missions, and research. Critics often question whether these resources could be better spent addressing urgent problems here on Earth, such as poverty, climate change, or healthcare. It's a valid concern, but it's also important to recognize the broader benefits of space exploration. Technologies developed for space, like satellite imaging, GPS, and medical imaging, have had transformative impacts on our daily lives. Investing in stellar research isn't just about understanding distant stars. It's about driving innovation that can improve life for everyone. Another ethical challenge lies in the potential militarization of space. As nations develop advanced space technologies, there's a growing risk that these tools could be used for conflict rather than collaboration. The fear of space becoming a new battleground is real, and it's a scenario that could have devastating consequences for humanity. This is where international cooperation becomes crucial. The Outer Space Treaty of 1967, signed by over 100 countries, sets a foundation for the peaceful use of space. It prohibits the placement of nuclear weapons in orbit and declares that space is the province of all mankind. While the treaty isn't perfect, it represents a collective commitment to keeping space a place of exploration, not exploitation. The importance of collaboration can't be overstated. Space is a frontier that transcends borders, and its exploration requires a global effort. Projects like the International Space Station, ISS, demonstrate what's possible when nations work together. The ISS isn't just a scientific laboratory, it's a symbol of unity, showing that even in the midst of political tensions on Earth, humanity can come together to achieve something extraordinary. This spirit of cooperation must extend to all areas of space research, from studying stellar remnants to exploring distant galaxies. At the heart of these ethical considerations is a simple question: what kind of future do we want to create? Do we envision a future where space exploration is driven by competition and conflict, or one where it's guided by curiosity, collaboration, and a shared sense of wonder? The choices we make today will shape humanity's relationship with the stars for generations to come. Reflecting on these challenges, it's clear that the study of stellar metamorphosis is more than just a scientific endeavor, it's a moral one. As we unlock the secrets of the cosmos, we must also strive to uphold the values that unite us: peace, equity, and a commitment to the greater good. The stars have always inspired us to dream, to explore, and to imagine a better future. Now, it's up to us to ensure that our pursuit of knowledge reflects the very best of who we are. Looking ahead, the future of humanity's relationship with the stars is filled with both promise and responsibility. As we continue to explore the universe, we must also reflect on the lessons it teaches us about our place in the cosmos, our connection to one another, and the legacy we hope to leave behind. The stars are not just distant points of light, they are a mirror, reflecting the choices we make and the values we hold dear. And as we gaze upward, let us remember that the journey to the stars is as much about who we are as it is about what we discover. The life and death of stars have long captivated not just scientists, but storytellers, artists, and dreamers. Stellar metamorphosis, with its dramatic transformations and cosmic scale, has become a rich source of inspiration for science fiction, weaving its way into the fabric of our cultural imagination. From the fiery birth of stars to their explosive deaths, these celestial phenomena have sparked tales that explore the boundaries of human understanding, the mysteries of the universe, and our place within it. Consider Christopher Nolan's Interstellar, a film that masterfully blends science and fiction. At its heart is the idea of black holes and their immense gravitational pull, which distort time and space in ways that seem almost magical. The film's depiction of a supermassive black hole, Gargantua, was based on real scientific data provided by physicist Kip Thorne. Its swirling accretion disk and the bending of light around it were not just artistic choices, they were grounded in the physics of stellar remnants. Interstellar didn't just entertain, it educated, sparking public interest in the science behind black holes and the life cycles of stars. Similarly, Carl Sagan's Contact explores the profound impact of stellar phenomena on human curiosity. The story revolves around the search for extraterrestrial intelligence, driven by the idea that stars and their remnants might hold the key to understanding our place in the cosmos. The film's iconic scene of a wormhole, a theoretical structure tied to the death of massive stars, becomes a gateway to the unknown, symbolizing humanity's yearning to connect with something greater. Through its blend of science and storytelling, Contact reminds us that the mysteries of stellar metamorphosis are not just scientific, they're deeply human. Beyond film, stellar evolution has inspired countless works of literature and art. In Arthur C. Clarke's The Songs of Distant Earth, the death of a star, a supernova, serves as the catalyst for humanity's interstellar journey. The novel delves into the emotional and philosophical implications of stellar death, using it as a metaphor for both loss and renewal. Meanwhile, artists like Vincent van Gogh have captured the awe-inspiring beauty of stars in works like Starry Night, where swirling patterns evoke the dynamic forces at play in the cosmos. These creative interpretations of stellar metamorphosis highlight a fascinating interplay between science and culture. They remind us that the life and death of stars are not just subjects of study, they are sources of wonder, symbols of the infinite, and mirrors reflecting our deepest questions about existence. By exploring these ideas through fiction and art, we gain new perspectives on the cosmos, bridging the gap between the abstract concepts of astrophysics and the tangible emotions of human experience. Yet, as much as science fiction inspires, it also drives us to seek answers in the real world. The same phenomena that captivate storytellers, black holes, supernova, and the remnants of dying stars, are the focus of cutting-edge scientific research. By studying these stellar remnants, we're not only unraveling the mysteries of the universe, but also connecting with the timeless human impulse to explore, create, and dream. As we transition back to the realm of science, let's delve deeper into the tangible remnants left behind by stellar death. These cosmic artifacts, from neutron stars to black holes, are not just the stuff of fiction. They're real, observable phenomena that continue to shape our understanding of the universe. And as we explore them, we're reminded that the line between science and imagination is often thinner than it seems. Now, let's turn our attention to an extraordinary role that stellar remnants play, one that might surprise you. Beyond their dazzling beauty and scientific intrigue, objects like pulsars serve as some of the most precise timekeepers in the universe. These spinning neutron stars, with their regular pulses of radiation, act as cosmic clocks, offering a level of accuracy that rivals even the most advanced human-made devices. But how exactly do these stellar remnants become the universe's stopwatch? And what does this mean for our understanding of time and space? Pulsars are essentially the remnants of massive stars that have gone supernova. When these stars collapse, their cores become incredibly dense, spinning rapidly and emitting beams of radiation from their magnetic poles. As these beams sweep across space, they create a pulsing signal that can be detected here on Earth. What makes pulsars so remarkable is the precision of these pulses. Some spin hundreds of times per second, and their regularity is so consistent that they can be used to measure time with incredible accuracy. One of the most famous examples of pulsars in action is the Hulse-Taylor binary system. Discovered in 1974, this system consists of two neutron stars orbiting each other, one of which is a pulsar. The pulsar's precise timing allowed scientists to detect subtle changes in its orbit, providing the first indirect evidence of gravitational waves ripples in spacetime predicted by Einstein's theory of general relativity. This discovery not only confirmed a cornerstone of modern physics, but also showcased the unique role pulsars play in probing the deepest mysteries of the cosmos. But pulsars aren't just tools for theoretical physics, they have practical applications too. In the 1970s, NASA Voyager spacecraft carried a map of Earth's location relative to 14 pulsars. These pulsars, with their distinctive pulse patterns, act as cosmic landmarks, providing a way for any potential extraterrestrial civilization to find our planet. It's a fascinating example of how stellar remnants can serve as navigational beacons, guiding us, and perhaps others, through the vastness of space. The precision of pulsars also has implications closer to home. Researchers are exploring how these cosmic clocks could be used to improve satellite navigation systems, like GPS. By comparing the signals from pulsars with those from satellites, scientists could create a more accurate and reliable global positioning system, one that's less vulnerable to interference or disruption. It's a testament to how the study of stellar remnants can have real-world benefits, bridging the gap between the abstract and the practical. Beyond navigation, pulsars are helping us explore the nature of spacetime itself. Their precise pulses can be used to test theories of gravity, measure the distribution of matter in the universe, and even search for dark matter. Each pulse is like a probe, carrying information about the fabric of the cosmos and the forces that shape it. In this way, pulsars are not just timekeepers, they are windows into the fundamental workings of the universe. Reflecting on these applications, it's clear that the study of stellar remnants is about more than understanding the life and death of stars. It's about unlocking the tools and insights that allow us to explore the universe in new and profound ways. From confirming the existence of gravitational waves to improving navigation on Earth, the legacy of pulsars extends far beyond their origins, shaping our understanding of time, space, and our place within it. As we continue to explore the cosmos, we're reminded that the universe is not just a collection of objects to be observed. It's a dynamic system, filled with tools and phenomena that can help us navigate, measure, and understand the world around us. And in pulsars, we find a perfect example of how the remnants of stellar death can become instruments of discovery, guiding us toward a deeper understanding of the universe and our place within it. Now, let's consider how these insights into stellar remnants are shaping the next frontier of space exploration, where the echoes of ancient stars continue to light the way forward. The story of stellar metamorphosis is far from over, and with each discovery, we uncover new possibilities for understanding the cosmos and our role within it. The life and death of stars don't just shape the cosmos, they also play a pivotal role in the potential for life itself. This is where stellar metamorphosis intersects with astrobiology, the study of life in the universe. From the creation of essential elements to the formation of habitable environments, the processes that govern stellar evolution are deeply intertwined with the conditions necessary for life to emerge and thrive. Let's start with the concept of habitable zones, often referred to as the Goldilocks zone. This is the region around a star where temperatures are just right, not too hot, not too cold, for liquid water to exist on a planet's surface. Water is a cornerstone of life as we know it, making habitable zones a key focus in the search for extraterrestrial life. But these zones aren't one size fits all. They vary dramatically depending on the type of star. Take red dwarfs, for example. These small, dim stars are the most common in the galaxy, and their habitable zones are much closer in than those of larger stars like our Sun. Planets orbiting within these zones, such as those in the TRAPPIST-1 system, experience very different conditions than Earth. TRAPPIST-1, located about 40 light-years away, hosts 7 Earth-sized planets, 3 of which lie within its habitable zone. However, because the star is so faint, these planets are tidally locked, meaning one side always faces the star while the other remains in perpetual darkness. This creates extreme temperature contrasts, raising questions about how life might adapt to such environments. On the other hand, massive stars like blue giants have habitable zones that are much farther out. But these stars burn through their fuel so quickly that their lifetimes are measured in mere millions of years. For life to develop on planets orbiting such stars, it would need to evolve at an extraordinary pace, a challenging prospect given the complexity of life as we understand it. Beyond the location of habitable zones, the life and death of stars also influence the availability of heavy elements necessary for life. Elements like carbon, nitrogen, oxygen, and phosphorus, essential for the chemistry of life, are forged in the cores of stars and scattered into space through supernova and planetary nebulae. Without these stellar crucibles, the universe would lack the building blocks for planets, organic molecules, and ultimately, life itself. Consider our own solar system. The elements that make up Earth and every living thing on it were created in the hearts of ancient stars that lived and died long before the sun ignited. This cosmic recycling process is a testament to the interconnectedness of stellar evolution and astrobiology. The death of one star becomes the birth of countless others, each carrying the potential for new worlds and perhaps new life. As we look to the future of astrobiological research, the study of stellar metamorphosis offers a roadmap for where and how to search for life. Missions like the James Webb Space Telescope are already peering into the atmospheres of exoplanets, searching for chemical signatures that could indicate the presence of life. By understanding the life cycles of stars, we can better identify which systems are most likely to host habitable worlds and focus our efforts accordingly. But the search for life isn't just about finding Earth-like planets. It's about expanding our understanding of what life could be. Could life exist in the extreme environments around red dwarfs or on planets orbiting white dwarfs? Could microbial life survive in the harsh radiation of a neutron star's influence? These questions challenge us to think beyond our own experience and consider the vast diversity of possibilities that the universe might hold. The role of stellar metamorphosis in astrobiology is a reminder that the universe is not just a place of stars and galaxies, it's a place of potential. Every star's life and death contributes to the cosmic conditions that might one day give rise to life, and every discovery brings us closer to answering one of humanity's oldest questions: are we alone? As we continue to explore, we're not just uncovering the secrets of the cosmos, we're also uncovering the potential for new stories, new beginnings, and perhaps new neighbors in the vast expanse of space. This interplay between stellar evolution and the search for life is a testament to the profound connections that shape the universe. From the birth of stars to the emergence of life, every step in this cosmic journey is a reminder of the beauty, complexity, and possibility that define our existence. And as we look to the stars, we're reminded that the story of the universe is still being written, and we are part of it. The story of stellar metamorphosis isn't just about individual stars, it's a thread that weaves through the entire fabric of the universe, connecting the smallest details to the grandest cosmic mysteries. By studying the life cycles of stars, we gain profound insights into the origins, evolution, and ultimate fate of the cosmos itself. From the fiery birth of stars in nebulae to their explosive deaths as supernovae, each stage of stellar evolution leaves a mark on the universe, helping us piece together the story of everything we see. One of the most remarkable ways stars contribute to cosmology is through their role as cosmic yardsticks. Measuring distances in space is no easy task, but certain stars, particularly Type Ia supernovae, act as beacons that help us map the universe. These supernovae occur when a white dwarf in a binary system accumulates enough mass from its companion to trigger a runaway thermonuclear explosion. What makes Type Ia supernova so special is their consistency. Because they all reach roughly the same peak brightness, astronomers can use them as standard candles to calculate distances to faraway galaxies. This method has been instrumental in mapping the large-scale structure of the universe and has even led to one of the most startling discoveries of modern science, the accelerating expansion of the cosmos. The discovery of cosmic acceleration, driven by a mysterious force called dark energy, wouldn't have been possible without these stellar explosions. In the late 1990s, astronomers studying distant Type Ia supernova found that they were dimmer than expected, suggesting that the universe wasn't just expanding, it was expanding faster over time. This revelation reshaped our understanding of the universe's fate, hinting at a future where galaxies drift ever farther apart, leaving behind a cold, dark void. But stars don't just help us measure the universe, they also provide clues about its origins. The Big Bang, the event that birthed the cosmos, left behind a signature in the form of light elements like hydrogen and helium. These elements, forged in the first few minutes after the Big Bang, became the building blocks for the first stars. By studying ancient stars, often called stellar fossils, we can trace the chemical evolution of the universe, piecing together how heavier elements like carbon, oxygen, and iron were created in the hearts of stars and scattered through supernovae. This process of cosmic recycling has shaped the universe into what we see today, enriching galaxies with the materials needed for planets, life, and even the stars of future generations. The interconnectedness of these processes is what makes stellar metamorphosis so vital to cosmology. Stars are not isolated phenomena. They are part of a vast, dynamic system where the death of one star becomes the birth of countless others. The elements forged in their cores become the seeds of new worlds, and the energy they release shapes the structure of galaxies and the expansion of the universe itself. It's a cycle that spans billions of years, connecting the smallest particles to the largest cosmic structures. Reflecting on this interconnectedness, we begin to see the universe not as a collection of separate objects, but as a single, evolving entity. Every star, every galaxy, and every atom is part of a grand cosmic dance, driven by the forces of gravity, fusion, and expansion. By studying the life cycles of stars, we're not just uncovering the secrets of stellar evolution, we're gaining a deeper understanding of the universe as a whole, from its fiery beginnings to its uncertain future. This perspective invites us to see ourselves as part of something much larger than our own world. The atoms in our bodies, the light from our sun, and the distant galaxies we observe all share a common origin in the life and death of stars. And as we continue to explore the cosmos, we're reminded that the story of the universe is still being written, a story in which we, too, play a role. Now, let's turn our attention to how these cosmic processes extend beyond stars and galaxies, influencing the very fabric of space and time. From the birth of black holes to the echoes of the Big Bang, the legacy of stellar metamorphosis continues to shape our understanding of the universe in ways that are as profound as they are beautiful. Throughout history, the life and death of stars have sparked wonder and imagination, inspiring stories and myths that reflect humanity's deep connection to the cosmos. Across cultures, the stars have served as more than just points of light in the night sky. They've been woven into the very fabric of cultural narratives, symbolizing creation, destruction, and the eternal cycles of existence. These stories, passed down through generations, remind us that the mysteries of stellar metamorphosis have always been intertwined with our understanding of the universe and our place within it. Take, for example, the Navajo creation myth, which tells of a journey through 4 worlds before reaching the present one. In this story, the stars are not just celestial objects, they are living beings, placed in the sky by the holy people to guide and protect. The Milky Way, known as Yikestahi in Navajo, is seen as a pathway of light, a bridge between worlds that connects the past, present, and future. This cosmic tapestry reflects the Navajos' reverence for the stars as both physical and spiritual entities, embodying the cycles of life and renewal that define their culture. Similarly, in ancient Greek mythology, the stars were often tied to tales of heroes, gods, and tragic love. The constellation Orion, for instance, is said to be a mighty hunter placed in the sky by Zeus after his death. His story, filled with triumph and tragedy, mirrors the dramatic life cycles of stars themselves, burning brightly, then fading or exploding in spectacular fashion. The Greeks also saw the Pleiades, a cluster of stars, as 7 sisters transformed into celestial beings to escape the pursuit of Orion. These myths, rich with symbolism, reveal how ancient civilizations used the stars to explain the mysteries of life, death, and the cosmos. In Hindu cosmology, the stars hold a different but equally profound significance. The nakshatras, or lunar mansions, are a series of 27 star constellations that guide the lunar cycle and are deeply embedded in astrology and spiritual practices. Each nakshatra is associated with specific deities, energies, and stories, offering a framework for understanding time, fate, and the interconnectedness of all things. Here, the stars are not just distant lights, they are active participants in the cosmic order, influencing both the heavens and the lives of those on Earth. Even in modern times, the stars continue to inspire storytelling, though the medium has changed. From science fiction novels to blockbuster films, stellar metamorphosis serves as a powerful metaphor for transformation, resilience, and the unknown. Stories like Star Trek and Doctor Who explore the lives of stars as both scientific phenomena and sources of wonder, blending myth and science to create narratives that resonate with audiences worldwide. These cultural narratives, spanning millennia, highlight a universal truth. The stars are more than just objects of scientific study. They are mirrors, reflecting our deepest questions, fears, and aspirations. Whether through ancient myths or modern tales, the life and death of stars have always been a source of inspiration, helping us make sense of the vast, mysterious universe we inhabit. Returning to the realm of science, these cultural connections remind us that the study of stellar remnants is not just about understanding the physical processes of the cosmos, it's also about exploring the human experience. As we delve deeper into the mysteries of neutron stars, black holes and supernova, we're not just uncovering the secrets of the universe, we're also connecting with the timeless stories that have shaped our understanding of the stars. This interplay between myth and science enriches our exploration of the cosmos, bridging the gap between the poetic and the empirical. And as we continue to study the life cycles of stars, we're reminded that the universe is not just a place of light and gravity. It's a place of meaning, wonder, and infinite possibility. The life and death of stars are not just topics for astronomers, they're gateways to understanding the universe, sparking curiosity and wonder in students of all ages. Stellar metamorphosis, with its dramatic transformations and cosmic scale, offers a unique opportunity to inspire the next generation of scientists, thinkers, and dreamers. By teaching stellar evolution in schools and universities, we're not just sharing scientific facts, we're nurturing a deeper connection to the cosmos and fostering the critical thinking skills needed to tackle the big questions of our time. Imagine a classroom where students explore the life cycles of stars, from their fiery births in nebulae to their explosive deaths as supernova. These lessons go beyond memorizing facts. They invite students to think creatively, solve problems, and see themselves as part of a larger cosmic story. Programs like NAS, STEM engagement initiatives, bring these concepts to life, offering hands-on activities, virtual simulations, and even opportunities to analyze real astronomical data. For many students, these experiences are transformative, opening their eyes to the possibilities of science and the beauty of the universe. One standout example is the Universe in the Classroom project, which provides educators with free resources to teach astronomy in engaging, accessible ways. Through interactive lessons on topics like stellar evolution, students learn not only about the science of stars, but also about the broader implications of their discoveries, how the elements forged in stellar cores make life possible, or how the remnants of dying stars shape the structure of galaxies. These programs don't just teach science, they inspire a sense of awe and curiosity that can last a lifetime. Universities also play a crucial role in advancing our understanding of stellar metamorphosis. Through research programs and observatories, students and faculty collaborate on groundbreaking projects, from studying the spectra of distant stars to modeling the dynamics of supernova. Institutions like MIT and Caltech offer specialized courses in astrophysics, where students delve into the intricacies of stellar evolution, often contributing to discoveries that reshape our understanding of the cosmos. These programs not only prepare the next generation of scientists, but also foster a culture of exploration and innovation. The impact of stellar evolution education extends beyond the classroom. Public outreach initiatives, such as planetarium shows and astronomy festivals, bring the wonders of the universe to communities around the world. Events like the annual International Observe the Moon Night or stargazing parties hosted by local astronomy clubs often feature discussions on stellar life cycles, making complex concepts accessible to people of all ages and backgrounds. These efforts remind us that the study of stars isn't just for scientists, it's for everyone. Looking to the future, the role of stellar metamorphosis in education is set to grow even more significant. With advancements in technology, virtual reality and augmented reality tools are making it possible for students to travel to distant stars, explore the interiors of supernova, or witness the birth of a planetary nebula, all from their classrooms. These immersive experiences have the power to ignite a passion for science in ways that traditional methods cannot. At its heart, teaching stellar evolution is about more than just science. It's about inspiring a sense of wonder and curiosity about the universe. It's about showing students that the stars are not just distant points of light, but dynamic, evolving entities that hold the keys to understanding our place in the cosmos. And as we continue to explore and educate, we're reminded that the story of the universe is still being written, and that the next chapter could be shaped by the students sitting in classrooms today. Now, let's turn our attention to how this growing interest in space education is shaping the future of exploration, where the lessons of stellar metamorphosis inspire new missions, technologies, and discoveries. The journey to understand the stars is far from over, and with each new generation of learners, the possibilities for discovery grow ever brighter. As we gaze at the night sky, it's hard not to wonder, could humanity one day live among the stars? The study of stellar metamorphosis doesn't just teach us about the life cycles of distant suns, it also offers a roadmap for our own future in the cosmos. From harnessing the energy of stars to transforming barren planets into habitable worlds, the possibilities for human exploration and colonization are as vast as the universe itself. But turning these dreams into reality will require overcoming immense challenges, from technological hurdles to the harsh realities of space itself. One of the most exciting prospects is the idea of harnessing stellar energy on a cosmic scale. Imagine a future where humanity has mastered the ability to capture and utilize the immense power of stars. Projects like Dyson spheres, hypothetical megastructures that could envelop a star to collect its energy, might sound like science fiction, but they're grounded in real scientific principles. While building such structures is far beyond our current capabilities, the concept reflects humanity's ambition to tap into the limitless energy of the cosmos. Closer to home, solar power from our own sun could play a key role in sustaining life on future space colonies, providing a clean and renewable energy source for habitats on the Moon, Mars, or beyond. Speaking of Mars, the Red Planet has become a focal point for plans of human colonization. Companies like SpaceX, led by Elon Musk, are already developing technologies to make this vision a reality. The Starship spacecraft, for example, is designed to carry humans to Mars and beyond, with the ultimate goal of establishing a self-sustaining colony. But living on Mars won't be easy. The planet's thin atmosphere, extreme temperatures, and lack of liquid water present significant challenges. To overcome these, scientists are exploring the concept of terraforming, altering a planet's environment to make it more Earth-like. While this idea remains speculative, it's a testament to humanity's ingenuity and determination to thrive beyond our home planet. The challenges of space colonization aren't limited to technology or environmental factors. Living in space also poses unique physical and psychological hurdles for humans. Prolonged exposure to microgravity can weaken bones and muscles, while the isolation of deep space travel can take a toll on mental health. Addressing these issues will require innovative solutions, from advanced medical technologies to designs for spacecraft that prioritize the well-being of their crews. Yet, despite these challenges, the potential rewards of space colonization are immense. By expanding beyond Earth, humanity could ensure its long-term survival, tap into new resources, and continue the legacy of exploration that has defined our species for millennia. The enduring fascination with the stars isn't just about survival or resources. It's about curiosity, discovery, and the desire to push the boundaries of what's possible. Throughout history, the stars have inspired us to dream, to explore, and to imagine a future filled with wonder. As we stand on the brink of a new era of space exploration, that sense of wonder remains as strong as ever. Whether it's the promise of new worlds, the thrill of scientific discovery, or the hope of connecting with other civilizations, the stars continue to call to us, inviting us to take the next step in our cosmic journey. As we reflect on the future of humanity among the stars, it's clear that the study of stellar metamorphosis is more than just a scientific endeavor, it's a source of inspiration. The life and death of stars remind us that the universe is a place of constant change, where endings give rise to new beginnings, and as we look to the future, we're reminded that our story is still being written, a story that might one day include new homes among the stars, new discoveries, and new horizons waiting to be explored. Now, let's turn our attention to how these ambitions are shaping the tools and technologies of tomorrow, from advanced spacecraft to cutting-edge research that could make life in space a reality. The journey to the stars is not just a dream, it's a challenge, an opportunity, and a testament to the boundless potential of human ingenuity. As we reach the end of our journey through the life and death of stars, it's time to reflect on the incredible story we've explored. From the fiery birth of stars in the heart of nebulae to their explosive ends as supernova, stellar metamorphosis is a process that shapes the very fabric of the universe. These celestial giants are not just distant points of light, they are the architects of cosmic evolution, forging the elements that make up planets, life, and even us. Every stage of a star's life tells a story of transformation. Their births illuminate the darkness of space, their steady burning sustains galaxies, and their deaths scatter the building blocks of creation across the cosmos. Whether they fade quietly into white dwarfs or explode in a blaze of glory, stars leave behind a legacy that shapes the universe for billions of years. Through their life cycles, we see the interconnectedness of all things, how the death of one star can give rise to countless others, seeding the universe with the potential for new worlds and new possibilities. The significance of stellar metamorphosis extends far beyond the stars themselves. It's a reminder of our own place in the universe, the carbon in our bones, the oxygen we breathe, and the iron in our blood were all forged in the hearts of stars that lived and died long before our solar system existed. As Carl Sagan famously said, "We are made of star stuff." This profound connection between the cosmos and ourselves invites us to see the universe not as something distant and separate, but as a part of who we are. But the story doesn't end here. The universe is vast, and its mysteries are endless. Each discovery we make about stars brings us closer to understanding the forces that shape our existence. Whether you're an avid stargazer or someone who's just beginning to explore the wonders of space, there's always more to learn, more to discover, and more to inspire. As we close this chapter, I encourage you to keep looking up. The night sky is filled with stories waiting to be uncovered, and every star has a tale to tell. Share your thoughts in the comments below. What part of stellar metamorphosis fascinates you the most? And if you've enjoyed this journey through the cosmos, don't forget to subscribe for more explorations into the mysteries of space. Together, let's continue to unravel the secrets of the universe and celebrate the beauty of the stars that light our way. Thank you for joining me on this cosmic adventure. Remember, the stars are not just above us, they are within us. And as we gaze at the night sky, we're reminded that the universe is not just a place of wonder, it's a story we're all a part of. See you among the stars.